This is the first set of videos for the career days for Advanced Algebra 2. This example was actually going to be presented on the last video, but we ran out of time, so we'll go ahead and talk about it now. We spent some time in that last video factoring polynomials and looking at the remainder theorem and the factor theorem of polynomials. The reason why we do that is because it helps us solve polynomial equations. And before we actually get into the practice of solving polynomial equations, I want to show you why it's important that we do so. And here's a real-world example. Suppose we have a polynomial that represents the population of an endangered species. If x is the number of years since 1990, we can then answer the question, when will the population become extinct? And if we graph a polynomial, the polynomial for this particular problem, we can use the graph to answer, and then we can verify that by using the factor theorem. So let's describe what we have here. Along the x-axis down here, we have the number of years since 1990. So if this is 0, this is the year 1990, and if this number all the way out here at the end is 27, that would be 27 years after 1990, or in other words, 2017. Now, the y-axis is the polynomial result, or the function result, and this was the polynomial given for this particular problem. Now, this axis represents the number of animals left in this species. And so what we can see happening is that in 1990, in this particular area here, we had a certain number of species. And if we were to evaluate the function or this polynomial when x was 0, if we changed each of these x's to 0, that'll tell us how many animals we had in 1990 for this particular species. And as it turns out, if we change x to 0, that changes each of these first three terms to 0. We had 768 animals in 1990. Now, as time progresses, the number of animals in this population decreases, and it hits a low point here. And we could determine what that year is, but that's not really what this question's asking. But we have a low point, and then the function turns and increases. We have a rise in the number of animals, and then for some reason that population starts to decline somewhere around this position. Well, again, that correlates to an x value, which represents a year. We could use that to answer a question if it was posed, but that's not what this question was asking. So we'll continue, and the population rapidly drops at this point until it reaches this value here. This is the value of importance because this represents 0 on the y-axis. This is a 0 of the polynomial. It represents when the population returns to 0, or when this particular population becomes extinct. That's the location of the answer to the question that's been asked in this particular problem. Now I'm going to erase my marks here so that we can see a little bit more clearly. If this value here was 27, then we can start counting backwards. This was 26, this was 25, and this mark represents 24 years after 1990. So to answer the question, when will the population become extinct based on this polynomial, the year would have to be 2014. In 2014, the population will become extinct. Now, what this is saying is that if I evaluate this function at the number 24, because that's 24 years after 1990, at the number 24, when I evaluate this function, it should be equal to 0. That's the function value. That's the position of the graph. It is 0 units above the x-axis. Now, based on the factor theorem, what we said earlier in our set of notes from yesterday was that if we had a factor with a number equal to 0, then that implies that x minus 24 is a factor of the original polynomial. And that original polynomial was negative x cubed plus 32x squared minus 224x plus 768. And that's pretty important for us. That's interesting because if we found one of our zeros, we know what one of the factors is. We can divide that out of this original polynomial, and then we'd have a better shot at factoring the rest of the polynomial if it can be done. So again, that's a very important feature as we move forward in this class. Now, to really answer this question, or to really use the factor theorem to verify, what we would want to do is show the math behind this calculation. So I'll set this up, but we can finish that, or you can finish that on your own by using the graphing calculator to verify. What we're looking for is what happens when we take the number 24 and cube that. Notice the negative signs on the outside of our parentheses here. That's how the original problem was given to us. We had a negative sign, then the number cubed. So negative 24 cubed plus 32, not x this time, we want 24. 32 times 24 squared minus 224 times 24 plus 768. And again, I'll allow you to enter these values into your calculator, and the end result you should receive is 0 because 24 was a 0 of this graph. Now to switch gears a little bit and look at this a little bit more algebraically rather than a real-world example, let's add these to our notes, and this will be helpful for you to complete the assignment for the career days this week. When we solve polynomials algebraically, we have to remember that factors of polynomials indicate zeros of a graph. And that means where the function equals 0, or in other words, that's where the graph crosses the x-axis, or where we have x-intercepts. That's what we just showed in that last example with the endangered species, where that graph crossed the x-axis is what we would call a 0. So what we're going to do in the rest of this video, and perhaps into the next, is we're going to find each 0 and verify those zeros by using a graphing tool. I'm going to use the TI calculator. You could also go to the website desmos.com, DESMOS.com. If you don't want to start up your calculator, that's a good graphing tool that you can use to verify these answers. Hopefully you've noticed at this point that any time that we're looking for a 0 of a polynomial, the first thing that we should do is try factoring the polynomial. And what we have here is a 4-term polynomial, and most 4-term polynomials, if they can be factored, would start off by being factored by grouping. So the first thing that I'm going to do is group these first 2 terms and the last 2 terms together and look for a GCF within each. In this first set, I see that x squared is common between x cubed and x squared, so I'll factor that out, and that leaves me with an x plus 1. Next, in the second group, I have a -1 that's common to both negative x and -1. So when I factor that out, I'm left with x plus 1. Our sign here changes because we divided by a -1. And that equation is equal to 0. Next, to finish the factor by grouping, we'll combine the coefficients, which are x squared and -1, and we'll represent this other factor one time as x plus 1, and that equation is equal to 0. Now you might think that we're done, but hopefully you'll recognize that we're not, because this term here, this binomial, can actually be factored again since it's a difference of 2 squares. And what I'll do is I'll call this x plus 1 times x minus 1. It's these 2 binomials that multiply together to equal this binomial. And we have the x plus 1 again left over. And while this is okay as an answer, I would like you to take it one step further. What we're going to show is that since x plus 1 is a factor that occurred twice, I'm going to list x plus 1 squared. Because, again, multiplication is commutative. We can go in any order, so that means I could multiply x plus 1 times x plus 1 immediately, And when I multiply a number times itself, that's the same as writing that number squared. And if I write that as a number squared, I'll include the other factor, x minus 1 equals 0. And this result tends to simplify our work just a little bit, and it makes a nice compact answer. We'll talk later in the next video about what this means to have a power surrounding a binomial. But essentially, it doesn't change the factors that we find for this problem. So I'm going to leave it like this. And I'm then going to go on and say that factors or zeros exist when x is equal to -1 or when x is equal to +1. And we know that because of our zero product rule, which we practiced last week or the week before. In order for an equation to equal 0, if it's factored, then any one of the factors could be equal to 0, and that would turn the rest of the equation equal to 0. So if x was equal to -1, this -1 in place of x here, plus 1 is 0. That 0 squared times the rest of the equation would equal 0. That's why we would say that -1 is one of our solutions. And for the other solution, we would say +1, because if we placed a +1 in place for x in this equation, when we get here, 1 minus 1 is 0. That 0 times this result over here on the left would again make the entire equation equal to 0. Now what this means for us is that when I graph the original polynomial, we should see that its graph crosses the x-axis at -1 and +1. So let's verify that. I'm going to switch to the graphing calculator here and allow me to readjust this window just a second. Actually, I'll leave that as it is. I think you can see the entire calculator here. I turned on a graphs page, and I've started here at the entry line, the function entry line. So what we'll have to write is the expression. This was x to the third power plus x squared minus x minus 1. So this is the polynomial that was given to us at the original problem. When I press enter to graph this, we should see that the equation crosses the x-axis in only those two positions. And there we go. Here the x value is -1. Here the x value is +1. Those are the two zeros that we encountered in our calculation on the other page. So let me copy this and put this over to the notes. Unfortunately, that moved some things around on my example, so we're still dealing with this function down here. It just got pushed to the bottom of the page. But here's the picture of the graph next to the work that we've done. I would encourage you to sketch a picture of your graph that represents this picture here, this graph, next to your work so that you can see how they're related. Again, what we said was that there was a 0 at -1. And there's a 0 at +1. So that's verified now with this graph. Something that's interesting that occurs is that this 0 at -1 occurred because this binomial right here, this -1 plus 1 would have equaled 0. And you'll notice that it had an exponent of 2 surrounding it after we simplified it. That exponent of 2 is what made this graph appear to approach the 0, touch that 0, and then turn away. So that's an interesting factor. Whereas with this other 0 in this position, x minus 1 produced the 0 at +1. This allowed the graph to cross through the x-axis and continue into the opposite direction. So we'll investigate that further as we move forward in the next video.